yourself, that doesn't exist. Well, maybe one of the five-dimensional black holes here. No, it's a way of representing it. See, it's like when you open a very simple book, especially popular science, and you see this representation of our universe as a sort of paraboloid that is expanding. And in the bottom of the paraboloid there is a point with a red color, say Big Bang. Well, that's a representation. Maybe God, if God exists, can say, look, that's the universe. Very well done, universe. I did it. But we don't know if that's possible. We've never seen, maybe it's possible, see? But we don't know. But this is a representation, right? All these very simple examples of Big Bang and expansion, they're representations. And they're very similar to the ones I'm showing you there, but they show the time evolution rather than the space form of it. They're representations. What these diagrams are showing is they are embedding the three surfaces of the rest frames in a space of higher dimension. But this is in order for us to appreciate the idea. So, doing the same thing here, this three-dimensional space is parameterized by small r, phi, which would be the angular coordinate here, and big R. See, it's three dimensions to represent 4, right? So I'm placing the hypersurface orthogonal to the 4 velocity in 4 dimensions. So what I see is that it is a foliation of 2 spheres. See, this is a 2-sphere. Here's another 2-sphere. Here's another 2-sphere, etc., 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 etc. Starting from the 2-sphere with 0 radius, which is the center, and increasing the radius of the orbits all the way, all the way, all the way. This is the form, this is the shape of this hypersurface. See? And this is a type of topology that is admissible for the models. It's the center of symmetry. And notice that R goes to infinity as small r goes to infinity as well. So that's what I'm telling you. The profile of R is increasing, 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 increasing. See, like this. So this structure is R3. It's equivalent because you can map every point here with a plane in this, see? Strictly speaking, R3 would be a plane in R4. But this surface has a topology of that plane. You can map it to a plane. It has the same topology of a plane. See? Okay, not the same curvature, but has the same topology. Okay? Now, this is the simplest topology that you can have. It's simply R3. And the physical meaning is that you have a place, a center, where the orbits are 0. That's a fixed point of the group. And you have orbits whose radius is increasing with an increasing radius. With an increasing, see, the radius R is increasing as the comoving radius increase. In terms here, what we would have, what we would have is that R is increasing as small r is increasing. And there is only one symmetry center. There's only one symmetry center. There's only one point where the orbits have 0 radius. See? So this is one possible topology.
So why can't it be understood as a paraboloid increasing in time?
What?
It can be easily understood as a paraboloid increasing in
No.
time.
No. we're not looking at we're looking, strictly speaking, at the rest frames.
Okay.
See? Yeah, you can do these sorts of things also in time, whatever. But no. Let's concentrate on this. It's important that you understand these possible topologies. Now, this is another one. This is the spherical topology. Here, what we would have is one symmetry center here, and then the orbits begin to increase. They reach a maximum value, and then they start decreasing until you reach a second symmetry center. So these models admit two symmetry centers. See, the FLRW models, the so-called closed models, are like this. Are like this. That's why many people like them, because the volume of the whole universe, the three-dimensional volume, is finite. See? So LTV models admit this type of topology as well. Okay? Here again, there's a symmetry center, then there is an equator, because this is a three-dimensional sphere that is embedded into R4. So it looks like a sphere. But I'm representing it as a two-dimensional. This is a three-dimensional sphere, which I have to represent as two-dimensional. Okay? So reaches an equator, then goes back to the symmetry center, the second symmetry center. So this topology admits two symmetry centers, right? Symmetry center is a locus where the orbits have zero area, or it's a fixed point of the rotation. Now, another topology, this is a wormhole topology. See, here there are no symmetry centers. That's also possible. It's a possible topology. This thing goes to infinity. Now, here in this case, here R equals 0, R equals 0 here is marking a symmetry center. Here, R equals 0 is marking the minimal throat, the minimal orbit. Here what you have is a collection of orbits, but the orbits are never 0. The radius of the orbits is never 0. This is a wormhole. Now, you can also identify these two spheres. You can make a topological identification with this one, and then you will have a toroidal shape, which is also possible. Right? See, this general relativity is local. Does not make any statement on the topology. It's only statements on the local curvature, right? But a given local curvature can be compatible with several topologies. These are three possible topologies that may have very similar local physics. Now, with LTV models, what we will see is that all models, either elliptic, parabolic, or hyperbolic, admit this type of topology. However, this type of topology, this is if lambda is 0. If lambda is 0, this type of topology is only admitted by elliptic models. Otherwise, you have singularities, or you have irregularities. And this type of topology is also admissible for hyperbolic models. That is, if you have two centers of symmetry in an LTV model without cosmological constant, then this thing must expand, bounce, and collapse. It cannot expand perpetually. You can devise a model like that, but it will not be regular. Okay? You can say, no, I insist, and I stand here on my horse, and I say, and stand on my ground, and I want to have the hypersurfaces of constant time with this topology, and I want this thing to expand perpetually. But then you will see that the model is irregular in several ways. It's not physical, the model. Okay? And the same thing happens here. this type of topology is only consistent if the evolution is elliptic, right? And then, of course, if you have a mixed region like that, then the topology is basically determined by the exterior. The topology is not local, it's a global property, right? And in this case, the elliptic behavior is only in a neighborhood, right? So the topology is essentially determined by the background. So a situation like this will have to have this topology, because this is the only topology that is consistent with perpetual expansion in LTV models without lambda. If you allow for lambda, then all what I'm saying goes out. If you have cosmological constant, then you can have all these topologies with every possible kinematic evolution, right? This is a nice feature of lambda. But without lambda, then the restrictions are, as I mentioned. Perhaps you don't, yeah?
How can we understand if we don't fix the theta equal to pi by 2 or something?
What?
What will happen when we don't fix the theta?
You can't represent it. Say, show me, and you get some sort of Nobel Prize. How you represent a three-dimensional surface in a diagram? Please show me.
Can we fix either one? Either one.
Ah, yes, yeah, I understand your point. Why fixing theta and not phi? Yeah, you can do that also, but it's easier to, because theta goes from 0 to pi, right? And then, like it doesn't cover, it's simply more practical, but you can also do that as well. What would happen there is that because phi goes from 0 to 2 pi, so this allows me to close the thing. Otherwise, it would be something that goes from 0 to pi, and it would not, for purposes of display, it's better to do that, but only for that. You can also do that as well, right? But you do have to fix one, otherwise it's good to represent, okay? Now, let's see. Spherical and wormhole topologies are only compatible with elliptic dynamics. That is, all regular ever-expanding models have the topology. Here, this twiddle means homeomorphic 2. Because topology, you identify classes. See, you identify classes that are homeomorphic classes of topologically equivalent spaces, right? So, this twiddle means belonging to the homeomorphic class of R3. See, all spherical and wormhole topologies are, these topologies are only compatible with elliptic dynamics. The reason is the consistency of the proper length along the radial rays. Radial rays are curves along the radial direction. These curves are orthogonal to the orbits, right? And they are space-like geodesics. So they are not just simply coordinate curves, they are space-like geodesics. And if you take the proper length along the radial curves, it's the integral of the GRR function. It's this integral, right? And the proper radial length along geodesics has to be a smooth and increasing function of R, right? See, if you have a geodesic and you compute the proper length along this geodesic, it cannot go backward, right? It cannot go backward as I increase the radius. It has to increase, and it has to increase smoothly, right? So if you set up this condition, right? If you set up this condition, then notice here that in spherical topology, R prime has a 0, and then it starts decreasing. And here it is increasing. It has a 0, and it's increasing again. It's decreasing and increasing and decreasing, but there is a 0. There is a 0 here. and there is a change of sign. So your proper length, unless k is positive, and it has to be, k has to be positive in such a way that it vanishes, k vanishes, k becomes 1 when r prime, do you see the point? In order for this thing not to change sign, you need k to be positive, right? There has to be some value where k is 0 when r prime becomes 0. Then this whole thing, by the L'Hopital rule, can remain an increasing function. So the necessary condition for this is that k can be 1 at some value. And this is not satisfied by parabolic and hyperbolic models for which k is 0 or negative. This is the reason why these topologies are not allowed for ever expanding models. Did you understand the reasoning? Did you see it? See, this thing, this integral, has to be a monotonic function, right? But in these cases, we have that r prime is changing sign. If k is 0, then the proper length will increase and then decrease. Proper length cannot do that. Proper length has to be increasing all the time, right? If I take my shoelace and I measure it like this, and I start measuring 10 centimeters, 20 centimeters, 30 centimeters, I cannot get 20 centimeters. See, I reach 30 centimeters, and if I go along the shoelace, it has to be 35. It cannot be 25, right? It's unphysical, right? If something like this happened, then my shoelace would not be physical, right? It would have to be discarded, right? So it's the same thing here. If k is negative or 0, then this whole thing will never be 0. And then r prime changes sign, and then your proper length will also change sign. That's not possible. So the only way to avoid that, and it's a necessary, not sufficient condition, the only way to avoid that is to have k being positive, strictly positive, and to that a value should exist so that this thing, by L'Hopital rule, can remain something that is perpetually monotonical, right? And so this means that this type of topologies are not compatible with 0 or negative k. So if you have an ever-expanding model, it must have this type of topology. This is when lambda is non-zero. I mean, when lambda is 0. Okay? So, in a sense, if you are modeling structure formation, you take only this type of topology and ignore these two. Now, Newtonian limit, the Newtonian limit, all Newtonian systems have this topology. Models with this type of topology have no Newtonian limit. There's no Newtonian equivalent. You can't describe wormholes with Newtonian physics. Full stop. Okay, so big pragmatic astrophysicist comes and tells me, who wants wormholes? We just want to describe galaxy formation. We don't want to describe wormholes. And maybe he's right. But nevertheless, it's nice to know that even that LTV models, as simple as they are, allow you to describe structures with wormhole topology. Now, there are some people who have examined whether this type of wormholes are transversable or not. In reality, they are not really transversable black holes, I mean wormholes, because it would take almost the age of the universe to transverse it. So don't worry, they are not going. This type of wormholes are not going to be used in science fiction or anything like that. But nevertheless, they are too big. The wormholes are too big, and then because they are only compatible with elliptic dynamics, they collapse. So you have to transverse them fast enough before they collapse. And then this means that basically that it takes you almost the whole evolution of the universe to traverse them. Anyway, That's another interesting point. In my first article was about this type of wormholes. And anyway, so that's why I'm so fond of them. Okay. Regularity conditions. We see this very fast. These are very technical issues. I just want you to know about them, but regularity conditions. First, regularity at the center. The locus T equals T Big Bang is R equals 0 for all R, and it marks the Big Bang singularity, right? However, big R can be 0 at small r equals 0 for all t. This is the symmetry center. Therefore, to allow for this, we have to make the following conditions imposed on the functions k, r, and tbb for in a neighborhood around r equals 0. These functions are arbitrary, but near r equals 0, they have to have this behavior. That is, r has to be of order r3, k has to be of order r squared, and tbb has to be a constant in any neighborhood near the origin. If you satisfy these conditions, then you can guarantee that big R will be 0 at small r equals 0 for all t, right? And this is, what we have here is that big R vanishes, but regularly, without singularities, because this defines the center of symmetry. Remember, the center of symmetry is an observer which is looking at all layers expanding away isotropically. It's like the center of the explosion, right? It's a spherical explosion. You are at the center, the exact center, so you see all the debris moving away from you isotropically, because you are in a privileged position. See, you are at the position of the fixed point of the orbits of the rotation wheels, right? Now, if you are flying away with one of these pieces of debris, then you are not going to see an isotropic explosion, because some debris will go close to you, moving slowly, and some debris will be moving very fast, and so on. But if you are at the center, then you stay put. You don't move. Everything is moving away from you. You stay put. Okay? Your radius, your big R is 0 all the time. And you are alive, right? You are alive. You are not in a singularity or anything like that. Okay? Well, so, models with elliptic evolution, that's another interesting point. See, models with elliptic evolution may have 0 or 2 symmetry centers, because you can have models with elliptic evolution with only one center, and models with elliptic evolution with 2 centers, with spherical topology. Okay? That's also possible. Now, singularities. Sufficient criterion for a curvature singularity is the divergence of any curvature scalar. For example, let's take this scalar. The Ricci scalar is equal to the density. This comes from Einstein equations. The Einstein equations for dust. See, dust is the only non-zero component of the energy momentum tensor, right? And this has to be equal to Einstein equations. So if you contract Einstein equations with a for velocity, you reach this equivalence. The Ricci scalar is identical to the density. But the density satisfies this formula, which is given by the field equations themselves. Remember the Lemaitre formula also. And this can be written in this way, because we can eliminate r prime, right? So we can identify now all cases in which this scalar, which is this one as well, blows up. let's look at the cases, right? There are several cases. One case is the Big Bang singularity. It occurs as time goes to Big Bang time and R goes to 0. Notice that R goes to 0 does not mean that R prime goes to 0, right? R prime goes to 0, but not necessarily R prime. R prime is not going to be 0 as well. Big R going to 0, right? This is a generic singularity. It occurs in all models. All models in the early time, they have a Big Bang singularity, which is a curvature singularity, and all curvature scalars blow up, right? Some models will have a second singularity, the elliptic ones. This will happen again, and it's a collapsing singularity, and it's called the Big Crunch. So I have the Big Bang and the Big Crunch. And in all cases, R goes to 0, right? Here, this one, it occurs in an early time, and this one, it's at a later time. It's a collapse singularity. See, this is as we have seen here. This is Big Bang time, and then these layers expand perpetually, no more singularities. But here, Big Bang time and collapse time, right? Here, Big Bang time, collapse, 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 collapse. These ones expand, Big Bang, no more collapse, right? But the collapse occurs when R goes to 0. Yeah, R goes to 0 for all at a given time, and it occurs for all observers at this time. What is the difference between the Big Bang singularity and the symmetry center? The difference is that the symmetry center occurs at a single world line, right? Only. While the Big Bang occurs for all the world lines at different times, but for all the world lines, right? So it's different. It's different. R equals 0, but under different conditions. Here, R equals 0, but without singularities. Here, R equals 0, but density diverges. And Ricci scalar diverges. Yeah, is that clear?
Sir,
Yeah.
you were saying for different Big Bang times you have,
Yes.
in that diagram, R is not going to 0 for different times, na? If R is not going to 0, we can't say that as a Big Bang time, can we?
No, R goes to 0. R goes to 0 at all these times. R goes to 0. What you can say is that for this observer, R goes to 0 at a certain time, which will be different from the other observer. See, for example, at this time, R is 0 for this observer, but it's greater than 0 for this observer, and so on, right? So a constant time will mark a singularity for only one of the observers, right? But there is a curve. There are times. There is a time where the Big Bang occurs for all of them. It just is not the same time for all of them. Big Bang is not simultaneous. Okay?
Okay.
Okay? You can change coordinates in such a way that you find a new time coordinate that will mark this as a constant value. Right? And then in that case you would say, yeah, the Big Bang occurs, but the problem is that such coordinate has no physical meaning, because the time coordinate that we're using is the proper time of the observers. Right? So it has a physical meaning. If you choose a coordinate in which the Big Bang time is forced to be simultaneous with that coordinate, it's possible mathematically, but then you lose the physical meaning of the time coordinate. See? Okay?
So it means, can we find a cosmic observer for whom the Big Bang has not still occurred?
Has what?
for whom the Big Bang has not still occurred, can we find out such a cosmic observer?
Maybe with 4 drinks of vodka? No. Why we know there's Big Bang? Well, the CMB, many physical indications, nucleosynthesis, etc. So, yeah.
So, can Big Bang singularity can be avoided in some models?
Can be avoided.
Yeah.
For example, with cosmological constant, you can have an evolution where the layers come from infinity, bounce, and return. There is no Big Bang. Yeah, with cosmological constant. Cosmological constant is 0, then it cannot be avoided.
And also with conformal quantization of the space-time metric in various space-time, you can show that
Quantization.
of space-time metric.
Yeah, but that's
That-
outside. That's outside of the theory. Yeah,
That can be showed in fact. That is,
There's quantum loop theory and several formalisms, quantum gravity formalisms that do away with the singularity. Yeah. Also, but you don't need to quantize. For example, the cosmological constant would remove the singularity in these bouncing models without quantizing. Also, if you have exotic matter, now that there is this notion of dark energy, all sorts of exotic model matters have been put in the table, which have no physics because it's only, well, they are based on physical assumptions and so on, but they are completely speculative, right? So, like Big Rip and ghost fields and etc. There are all sorts. It's a fauna of exotic matter that will avoid singularities, right?
Or by adding higher order derivatives of scale factor.
High order what?
Higher order derivatives of scalar field.
Yes, with scalar fields you can construct models that will. Yeah, that's what I'm saying. See here, if I put cosmological constant, I'm sort of modifying the source, right? In a very simple way, and you already removed. Now there are many ways in which you can put sources that will change the evolution. See, we'll see that in a minute. We'll see the justification for this in a minute, right? Now, these are generic singularities. Big Bang, it's not a problem because there are many evidences that there had to be some very, very hot, violent, critical event in the past of the universe. For example, the cosmic background radiation, which is a remnant. It's a photon gas that cooled down to 2.7 degrees Celsius. Then the nucleosynthesis. There are many evidences that we cannot observe the Big Bang, by the way, because what happens is that any photon that comes to our eye or to our instruments, it's a photon that must have traveled for distances that are much less than the Big Bang. When I say traveling distances, I mean times. There was, we know, and there are many indirect evidence suggesting this, that there was a time when the photons were very closely bound with electrons and with, especially there was a time when there were no galaxies, there were no planets, nothing like that, and all of cosmic matter was a plasma. It's called a radiative plasma. It's a plasma made with photons, electrons, protons, and neutrons, all of them without atoms, or no bound atoms, just the particles in thermal equilibrium. Now, in such plasma, there's a very strong, the photons are very strongly tied. What I mean strongly tied? They interact very strongly, especially with the electrons. This is a Thomson scattering, and Compton scattering. They are very well-known processes that can be even reproduced in plasmas, earth-bound plasmas. And so the photons are very busy. So these photons have not reached us because they were playing with the electrons, right? So once this plasma becomes cold enough, this interaction stops. It doesn't stop completely. There are but let's say it mostly stops. And then atoms are formed. The electrons are captured by the protons and the neutrons, and the atom formed. And so the electron tells the photon comes and says, hey electron, let's play. And the electron said, no, I'm sorry, I am here in my atom, with my nucleus, so go away. So poor photon goes away, and it reaches us, right? But that's not a photon from the Big Bang. It's a photon that came 300,000 years after the Big Bang, when the radiative plasma became cold enough to form atoms, and therefore the photons had nobody to play with, so and they came all the way. This is a cosmic microwave background that we cannot observe before. The universe was opaque. It was not it becomes transparent 300,000 years after the Big Bang, and then we can see. That's as far away as we can see, right? Now, Big Bang is a generic singularity, big crunch. They are okay. We have no problem with these singularities.
But as you approach to as t goes to 0, then curvature scalar will go to infinity.
Yeah, but let's say...
No, what I would like to ask you then, can we have some gravitational waves effect?
No, not with these models, no.
No?
No, not with these models, because they're, as I said, these are Coulombian fields. They're Petrov type D. They have no magnetic Weyl tensor. We cannot have gravitational waves with these models. No, it's ruled out. We cannot have magnetic fields either. Okay. Now, there is another type of singularity, and this is a problematic singularity, because this is a singularity that occurs because of the model. See, these models are dust. Dust implies there is no pressure, implies there is no internal motion of the particles. And it's an approximation that it is a reasonable approximation if the density is not very high. We have a fluid that is diluted. We can say that the effects of internal pressure are negligible in comparison with the rest mass, right? What happens if the density becomes large and large and large? Then this approximation is no longer correct. And one of the ways it shows up is in the emergence of a curvature singularity that is called shell crossing. What happens is that you have two comoving shells whose coordinates are different, right? And they remain different because the coordinates are assigned in this way. See, you, the problem. You are carrying the coordinate label r equals 1. Here. Carry it on. This is your flag, right? R equals 1. And I'm r equals 1.1. We're different, right? So we evolve. Hi, how are you? We evolve. Okay. There comes a point that density is large, so we get close to each other, yet you are reading the coordinates. You say, but you are different. He's 1.0, you are 1.1. But nevertheless, these are coordinates only. But the proper length between us starts across until we crunch to each other. And so over there, the Ricci scalar said, oh, I'm infinite. Right? But you that were measuring coordinates say, how come? They are different. But and this is the shell crossing. Two shells cross each other. They have different coordinates, right? But the shells cross each other from the evolution. And this is because, thanks coordinate, thanks applause for the coordinate here. Okay. So you see, this arises because dust is no longer a good model. And then shells can get very close to each other, even though they have different coordinates. The different coordinates are starting to label the same point, and the shells cross like this. And this is a non-physical singularity. Well, in some cases it can have some physical, not in spherical. In spherical symmetry, some physical. You know, as we will see with Sekker's models, the shell crossings, they start to be physical. They become, again, physically important. But here, the spherical symmetry is completely unphysical. Now, what we have is that for models with spherical and wormhole topology, notice that this gradient, big R gradient, can be zero under regular conditions, but this can only happen at a finite sequence of fixed comoving values. You remember the topology, spherical topology, like a ball, remember? So in the equator, R prime is zero, but this is regular, right? Because when this happens, K has to be 1. So it's regular, right? Okay, what happens in those cases? Well, we'll see that here. What happens in these points, these are like turning values, is that this thing, and this thing, and this thing, and this thing have to be 0 when K equals 1, right? Notice here, K equals 1 when this is 0. R prime is 0 when this one on top is 0. Therefore, this thing remains finite, right? And this is only possible with elliptic dynamics, right? As I mentioned before. Now, what happens when this thing here, R prime, goes to 0, but M prime does not go to 0? This thing blows up, right? And the proper length is proportional to R prime. So when R prime vanishes without K being 1 or M prime going to 0, the proper length crashes, goes to 0. See, and the shells collide. They cross. The shells cross. And when this happens, see, points where R prime goes to 0 that are not a comoving Bohr line, which means M prime is not necessarily 0, then we have a shell crossing singularity as GRR, the metric component, goes to 0, and rho goes to infinity when big R is greater than 0. So anyway, these are technical things. You can, but the point you have to understand is that it can happen that R prime, big R prime, becomes 0 under special conditions that are different from these zeros in the topological case. And in this case, you do have a singularity. But that singularity is not physical. We would like to avoid it, at least in spherical symmetry, right? And there are conditions. The conditions to avoid the singularity are here. When you choose your functions R, M, K, and TBB, you must request these conditions, that whenever R prime vanishes, M prime also vanishes. If M prime never vanishes, then R prime should never vanish. And this is the regularity conditions with which you choose your, when you choose your functions, you have to choose them so that they satisfy these conditions, right? These conditions can be, the conditions to avoid shell crossings are completely expressible in terms of the three parameters, M, K, and TBB. There are choices of M, TBB that you can choose in such a way that shell crossings never arise. It's also possible, but anyway, what I just wanted to describe it. Now, for models with open topology, which are all ever expanding models, the necessary and sufficient conditions to avoid shell crossings is simply to demand that R prime, big R prime, is greater than 0 for all coordinate values for which r itself is greater than 0. And this condition is equivalent to, you have n prime to be greater or equal than 0, k prime to be greater or equal than 0, and TBB to be smaller than 0. These conditions, for ever expanding models, these conditions assure you that there will not be short crossings, right? But then there is a restriction on the free parameters of the models, right? You are constructing models of this type, you want to avoid short crossings. These are the conditions that you have to. Yeah. Any question? Yeah.
So in open model, there is possibility of big rip singularity.
Sorry?
In open model, open topology, there is possibility of big rip singularity.
No. These models have no big rip. These models have no big rip.
What
No.
is the reason, sir?
Because what big rip is when you get the singularity asymptotical in the future, right? Or you have an evolution the layers are evolving and suddenly they become singular. But it's not a shell crossing singularity. Big rips occur only when you have when rho plus p is negative, right? It's not 0, but it's negative. Here you don't have. No, the dynamics of the model do not allow for big rip. Not here. Not here. This is not exotic enough. This is a very simple model. We have a saying in Spanish, don't try to look for a cat having 3 legs.
Another question. These models shows the acceleration also.
What?
These models shows acceleration also.
Yeah, acceleration, you can see it here. There's one way of looking for acceleration is R double dot, right? R double dot, here R double dot will be positive. Well, these models are collapsing. But among the expanding models, they're all decelerating. If cosmological constant is 0, all these models decelerate. They expand, but in a decelerated way. Now, if you have cosmological constant, then you will have acceleration in large times acceleration. Yeah, that's true.
So
But otherwise, they decelerate.
So those models which will accelerate for large value of R, those will again collapse.
No. They don't collapse. They accelerate. If cosmological constant is large, then the models would evolve like this, no? And then here you can see the concavity would be positive. The second derivative is here. Second derivative is negative. The models are decelerating, right? Second derivative is negative. If you put cosmological constant, then it does like this. Second derivative is positive. There's no big rip because density will decrease to 0 very fast. Curvature will decrease to 0. Big rip you need in the future, singularity in the future. That's not going to happen with this model.
In that case, they will ever accelerate.
With cosmological constant, yes. Okay. Without cosmological constant, is ever decelerating. Okay. Now.
Can you just repeat that spherical wormhole topology? That thing.
What?
That for model with spherical and wormhole topology.
Yes.
Yeah. So here, what exactly we are going to? Just I cannot understand that if you put R dash equal to 0.
R what?
R dash is equal to 0.
Yes. Well, because of the topology, because of the way the surfaces are. See, if you have spherical topology, then what is R doing?
Yeah,
It's doing like this. If you plot it as a function of small r, it's doing like this.
yeah,
Then there is a point where it will be 0.
yeah.
But if you set these conditions, goes to 0 when k equals 1, and all these things also vanish, then this will not make this quantity diverge. What you have to check is that this quantity remains finite and smooth. Now, if r dot becomes 0, how do you manage to get this thing not diverging when r dot goes to 0? Well, you demand that m dot goes to 0 at the same point. And then you apply local and it remains smooth. Another way is to demand that k equals to, that k goes to 1, right?
Yeah, yeah.
And then all these things you have to do in order to prevent that term from diverging, right? R prime appears in the denominator, therefore you have to juggle with the numerator, right?
Okay.
And then you avoid the singularities by
Putting this condition.
yes, by putting this condition. Now, if you don't put them, then you get this shared crossing singularity. Okay. Now, you cannot do the same thing when k is 0. Then the only way you can avoid the singularity is by demanding that r prime is always increasing, that m prime is always increasing. And then you avoid, that's the only way you can avoid them, right? Because you cannot juggle with a numerator, with a denominator or with a numerator in the case of ever expanding models, right? Okay? That's it. That's no more than that. Okay? Now,
Sir, you said now m is equivalent to mass of the system, mass of the universe, or mass of the system?
it's a sort of mass, but we will see that. Now, you can think that m is a sort of mass. Now, notice that in general relativity, you can have several definitions of mass.
Seven definitions.
Yes, yes, you have proper mass, and have the quasi-local mass, you have the Hawking mass, the ADN mass. There are several definitions of mass.
Depending on the location of the mass?
No. Depends on how you define them. For example, volume. Say, volume, this proper volume, which is the integration, right? Is the integration. You have a region, compact region, and you start integrating slowly, you get certain volume. Now, that's one volume. Now take a closed surface, like a sphere, and then obtain the area of that sphere, and then you say, well, if this is the area, I can obtain the radius, and if I cube the radius, I get a volume. Well, that volume is different from the proper volume. In flat space, no, but in curved space, it is. It's the volume that you get from a surface, say, from a surface area, you can get a volume. That volume is different from the volume that you get by integrating. Because when you integrate, the metric is varying in different ways. If it's all the way from the center to the surface, than if it is only evaluated at the surface. We'll see that. We'll see. M, I promise you, it's very important. M,
I was asking this because you were saying M was in that kind of model, M was increasing. In ever expanding models,
Yes.
M was increasing. How
Yes.
can it be possible? If it will be the just mass, then
No,
at the point of
it's the mass for a given see, it's a mass that characterizes a dust layer, right? We have a pile of dust layers, spherical dust layers that are expanding, right? So each one of these layers corresponds to a two-sphere, right? And it is labeled by a value of small r. Small r is a label for all these spherical layers, right? Okay, and m refers to the mass of that layer. The next layer will have a different mass, and the next one will have a different mass and a different mass, and so the mass is increasing for this pile of layers. It's very simple. You yourself are one layer, right? and you have a mass, right?
Hmm.
I think you are not a photon, so you have a mass, right? Okay, now your bodies around you, they define the second layer, right? And they have a mass. So the second layer will be your mass plus their mass. Then you take the next bunch of layers, and the next, and as you take more and more and more layers, the mass contained internally is increasing, isn't it?
Yeah. It's a function of R.
But
It's a
sir,
function of R, yes.
if you are thinking about an expanding universe,
Yes.
for which initially all the mass was at one place at the time at the time of Big Bang, all the mass was here, and then it exploded and the mass started distributing. So net mass should remain the same now.
No, but that's a bad analogy, because you are thinking of a homogeneous space-time. Here, first of all, here, Big Bang is not simultaneous. There is not a single time
Yeah, single.
where everything was zero. Big Bang is not simultaneous. So what you can say is that at this time, all this layer have zero radius, but that layer was already. It's not a good
For
analogy. No,
different
look.
layers, you can have different Big Bang times. You mean
Yes,
here.
yes. See, this is not a nice thing to, because it's sort of counterintuitive.
Yeah.
It's counterintuitive, but be patient and say, we'll see. We're going to define the mass as an integral of the density very soon. Okay, yeah.
Sir, you said when we trying to pass a wormhole, they collapse.
These wormholes collapse, yeah.
Means they are unstable.
No, they are not unstable. Because unstable is if the wormhole is like this and can suddenly collapse. This is not a sudden collapse. It's a collapse you can predict. And
Systematic.
it's a very slow collapse.
After some time.
After a time that is almost the age of the universe. Right? So, LTV, I don't know if we have time. How much time we have? Half an hour.
Yeah.
Okay, so we have half an hour, yeah, because this is an important. Here I'm going to see the effects of the cosmological constant.
You want copy? I can.
Okay. So, effects of cosmological constant. So far, we've assumed cosmological constant to be zero. These are LTV models. Now we're going to see the LLTV models. What are those? The lambda LTV models. Okay. See, the Friedman-like equation is now going to be a more complicated equation because we have a cubic term. And of course, the evolution is going to be much more complicated. See, just to appreciate this, let's look in the blackboard. See, our equation, our Friedman equation, was something like this. Right? Very simple. Yeah? Now, more complicated. More complicated. And one complication we have is that what happens when R goes to infinity? When R goes to infinity, this is negligible, this is negligible, and this is dominant. So, in this case, this is, what's the solution of this? It's an exponential. Right? It's so R is approximately exponential of right? What is this? The theta. So these models are, the other models were asymptotically Minkowski. Far away, they become asymptotically Minkowski. Because if lambda equals 0, then asymptotically R is a function of t, which is a Milne spacetime. Okay. But if there is lambda, then asymptotically we have an exponential expansion. In fact, it's like sort of inflation. It's an inflationary behavior asymptotically, right? If lambda is greater than 0. But not only that, now this is when R is very large. And what happens when R is about 0? When R is about 0, this term negligible. This term negligible. This term dominant. Right? So, again, what we see is that when for R very small, the cosmological constant is irrelevant, doesn't matter. It's the same behavior. See, the effect of the cosmological constant is only important for large values of R, right? So models that collapse very fast, they are practically identical. Cosmological constant makes no effect. Cosmological constant is important for models that, well, maybe models that collapse but take a long time to collapse is also important, or models that never collapse in their faraway time regime. Then cosmological constant is very important, right? But notice that this equation is much more difficult to solve. Like, say, what happens in, say, we have this. This is the equation we have to solve. But notice that inside of the square root we have a cubic polynomial, which means that if we try to solve this analytically, we get a hyperelliptic function. Well, actually, no, we get, it's a sum, it's our elliptic integrals of the first and third kind, which is already quite nasty to work with them. Anybody who has worked with elliptic functions, believe me, in my PhD, I had enough with elliptic functions. They are very nasty, elliptic functions and integrals. Notice how this is much harder than if lambda equals 0, then the equation we had to solve before was this one. And this one is quite manageable. And I already showed you the analytic solution. This one, better do it numerically. Okay, so let's see the effects of cosmological.
Sir,
First, yeah.
can you please give me an example of the situation where you would need to include a cosmological constant to any equation? I mean to say that real life example. Real
Well, real life example.
means to say physical example.
Well, look, you are looking at supernovae, right? You assume zero cosmological constant. Then observations are not fit. So, well, you have to bring the, there are other approaches. You don't have to put cosmological constant. Cosmological constant is the simple of this approach. Cosmic age. Remember the first lecture? We saw Friedman rods and Walker models. If you assume that all you have is dark matter, and there is no cosmological constant, then you cannot fit cosmic age. So this is one of the reasons people bring it.
You mean to say that cosmological constant means something unknown coming into the universe, which we don't know?
No. Cosmological constant is allowed by Einstein equations, right? It's allowed by Einstein equations. You remember when I derived Einstein equations? When we derived Einstein equations, we use this reasoning.
In fact, it's a creation of Einstein only, no? He supposed that we should have cosmological constant.
Yeah, but that's besides the point. But why he supposed it? Because it's allowed.
Yeah.
See, you have energy momentum tensor, right? The divergence of this thing is zero, right? But also we know that the divergence of the metric tensor is also zero. This is by definition,
Yeah.
because that's the way you construct the Christoffel symbols and everything, okay? So this is known. Now, Einstein proposed these equations, because these equations relate curvature to sources. But this has to satisfy this constraint. Right? Has to satisfy this constraint as well. And this is zero, and this is zero. This meant Einstein was looking for a tensor that had to have zero divergence. Now, suppose you check, suppose you assume this thing. You can find out that the simplest tensor that satisfies this is this one. Right? It satisfies this. So that's Einstein's tensor. But what happens if you add a constant, if you add to this a constant times GIV? It also satisfies. So really, the most general Einstein's tensor would be this one. Okay? The most general. Okay?
It is as good as saying decomposition of Einstein's equation.
Sorry?
As a
What?
Isn't it like decomposition of Einstein's equation?
No. Don't look for cats with 3 legs. Don't look for cats with...
Please.
It's an addition, no? Cosmological constant is addition. You are not doing anything with that.
Actually, he wanted a static solution.
Yeah.
The mathematics allow it. Now, is it physical or not? Well, or maybe you can, instead of putting the cosmological constant in the geometry, this is the geometric side, right? Here I'm putting the cosmological constant in the geometric side. But you can also put it in the other side and assume it's a source.
Yes.
It's equivalent, mathematically at least. Now, why Einstein used it? Because when he's...
Static solution.
Yeah, because in his times, there was no evidence the universe was expanding. In his times, the cosmography of the universe, that is the description of the universe, was based on this idea of the universe island. Yeah, planets and stars, they move. but there are, on average, the whole system is static in an island. So when Einstein tried to use apply to construct Friedman models, FLRW models, with dust, he saw that the only way to force a dust FLRW model to be static is by adding a cosmological constant. And that's why he proposed it, in order to get an FLRW static model with dust. Okay? The only way you can do it, as I will show you now, is with cosmological constant. Cosmological constant, you can have an FLRW model or a dust model, even if it's homogeneous, that is static, with a cosmological constant. And then Einstein said, well, that's it, fellows, let's go launch. Okay? But then the Hubble and other astronomers show the universe is expanding. And then is when Einstein said, oh, big blunder, big blunder, right? But that's because, see, you take the cosmological constant because you think that it will be compatible with measurements, right? Now, why recently people think of cosmological constant? Because supernovae, observations, and so on. So those are the reasons whether to take it or not to take it, okay? Now, let's start moving around here. The quadrature is horrible. It's an elliptic integral, third order, best to look numerically. But what we're going to do is to appreciate qualitatively the evolution. So we rewrite these Friedman-like equations as a Newtonian energy equation, and we look at the energy diagram. This is very important. Please concentrate very well on what I'm going to show. This is the energy diagram. What I'm doing is I'm rewriting this Friedman equation, which you can see here. I'm rewriting this equation as an energy equation. That is kinetic energy, a potential, which will have this form, and total energy, right? So K minus K plays the role of the total energy. This plays the role of a potential. Now in an energy diagram, which we have all seen, then the possible evolutions are these places. These are the possible evolutions. This is a forbidden zone. This is a forbidden area because R dot squared would be negative. So it's a forbidden area. This is the potential. And this is a potential when there is cosmological constant. This is a potential when the cosmological constant is positive. We're going to assume it to be positive, not negative. Okay, never. And this is the potential when the cosmological constant is 0, right? So what happens when the cosmological constant is 0? What happens is that all models, this is the case where the energy is negative. The binding energy is negative, therefore K is positive. See, when cosmological constant is 0, whenever you have positive K, the models expand, bounce, and collapse. Expand, bounce, and collapse. Expand, bounce, and collapse. Expand, bounce out, and collapse. When K becomes very close to 0, then the bounce may take a long time, but nevertheless, it happens, right? This is the marginally bound case. 0 energy. This is for the potential here with 0 cosmological constant, right? So here, all models for which the binding energy is positive or K is negative, they perpetually expand, right? Of course, they slow down, but they expand, right? Now what happens when we put cosmological constant? The potential is identical for small, is undistinguishable. If r is small, the potential, this term plays no role, and the potential is the same. Notice that the potential for lambda 0, the potential is 1 over r. Very simple, attractive potential. Now, when you add a cosmological constant, then the potential is attractive for small r, and then it becomes repulsive. This is a repulsive potential for large r's. And then there is a point here, a sort of saddle point here. And so the evolutions that you can have are very different, because you can have models with k, with positive k, that are ever expanding, right? That was not possible before. Now it's possible. Models with positive spatial curvature that are perpetually expanding, right? And you can have cases of models that come from infinity and bounce, and therefore avoid the Big Bang, right? And you can have also models that behave as in the case lambda equals 0, they expand, bounce, and collapse. And all models, you can have ever expanding models for positive k and for negative k. But for positive k, you can have ever expanding models. This is why you can have topologies that are, spherical or wormhole here, because k can be negative. I mean, k can be positive and still support ever expansion. See? If lambda is 0, ever expansion is only possible if k is 0 or positive or negative. Right? It's only possible in this region. If lambda is 0. But if lambda is non-zero, then ever expansion is possible in all this region, which includes cases with positive k. Therefore, all the regularity problems we had with the proper length go away if we have lambda greater than 0. And big surprise, we have a static state here, but it's unstable. It's an unstable equilibrium here. This is Einstein's universe. But for having an Einstein's universe and static case, you need cosmological constant. Otherwise, there's no cosmological constant. The potential is always attractive and has no stable, no unstable equilibrium, right? Here you have an unstable equilibrium. So you can have a model that emerges from the Big Bang and sits here, terminates here. Or you can have models that come from infinity and settle down here. But this is unstable. Minor variation and either collapses or expands. So it's extremely unstable. So Einstein's universe is extremely unstable. Here's Einstein's universe. And Einstein is there celebrating and having fun in some tavern in Switzerland and so on, is having fun. Suddenly I come, here's his universe, and I do. Go! See? This is unstable in the sense the wormhole that I say is not like that. This is an extremely unstable situation, right? So notice how the fact that we have a cosmological constant gives us a lot of degrees of freedom that we didn't have before. Namely, this is what I've been saying is condensed here. In the case lambda equals 0, all models that have a negative or 0 k are ever expanding. But when lambda equals 0, there are ever expanding models with positive k. See, this is the shaded area. These are all the models that are ever expanding that are possible with a cosmological constant. And this includes models with positive k. As a contrast, when lambda equals 0, all models with k greater than 0 expand and collapse. All this, if cosmological constant is 0, all these models would expand and collapse, right? So this is a major change. Second point here. Ever-expanding regular models with spherical or wormhole topology are possible if lambda equals 0, if lambda greater than 0, for the reasons I've mentioned as well, right? There is no regularity problem with the proper length of the space like geodesics. And for early times, near the Big Bang, the effect of lambda is negligible. But the effect is crucial for large values of R. For large values of R, the potential is already repulsive here, and it is still attractive here. But for small values of R, the potential is attractive and is practically identical in both cases, right? So I think this is very important. I think we should make like a 10-second now.
Yeah.
I'm not here. Think about it. Take your time while I sip my coffee.
And also when you talk about collapse, then it doesn't affect, we have said about horizons structure changes completely.
Yeah, well, that's an interesting point.
Yeah.
Like, if the collapse is very fast, there is no effect. But,
But
for a
it will
slower collapse,
slow down the collapse because of repulsive force of cosmological constant.
No,
Initially, at least.
No, and it will also, yeah, because if the collapse takes some time,
Yeah,
then there is an effect here. There is
yeah,
an effect.
because there is a repulsion. But horizon structure changes very drastically.
Yeah, for large distances, but it also affects the collapse. In
Yeah.
fact, once you solve this equation, you can see that the collapse is slower.
Slower, that's right, because of repulsion.
And this is an important point when you are trying to model structure formation.
Yeah.
Now, structure formation, people who do that, they assume that the cosmological constant is not very important in small regions. Because you can ask, is a cosmological constant important, say, for solar system? No. Solar system? Is it important for galactic dynamics? No. It is important only, it becomes important only for very large superclusters. And it is still questionable. So, but nevertheless, there are some people who have put cosmological, when they do numerical simulations, cosmological constant enters in the boundary conditions only. It's not used in the local dynamics. But it's interesting that the LLTV models are useful also. In fact, the problem is that these models, the lambda LTV models, cannot be worked analytically. If you work with that,
For k is equal to 0, you can get solution.
yeah, very close to 0 because it's so similar.
Yeah, because k is equal to 0 gives analytical exact solution. Once you put k non-zero, then it's a problem. Because mathematically, it's become impossible to solve.
Now,
But k is equal to 0, yes.
There are some cases with lambda greater than 0 where you can get analytic solutions. It depends on the
No, I'm
cubic-
saying k. If you take marginally bound case,
yes.
the exact solution is
No, that's what I was going to say.
Yeah.
See, if you look at the cubic polynomial Q,
Yeah.
this cubic polynomial, and if you make k equals 0,
Then solution
then
is
it's a very simple,
yeah,
and then you have
analytical.
and also, in the near static case, it's also very
Yeah,
simple.
yeah.
Because of the mathematics of the cubic. See?
Cubic, yeah.
See, it's an equation of this type. See, we have a cubic polynomial here. This is a cubic polynomial divided by R. Now, this cubic polynomial takes the form 2m plus something like this. Then this is like a quadratic. This is a very simple case. This thing can be written as and then this integral simplifies. This integral simplifies to r dot equals square root. Something like this, right? This has an analytic solution because the cubic polynomial is very simple, right? And then it also, if the cubic polynomial has this form, something like if the cubic polynomial has this form, then it also simplifies. And this corresponds to the static case, and this is the case with the zero curvature. For these cases, there's an analytic solution, but only for these cases. Otherwise, no. Otherwise, it's a sum of a first order elliptic integral times a third kind. First kind and second kind becomes completely untractable.
Okay.
Completely untractable. So I think it's a good time to stop now. Okay?
Yeah. Afternoon, we can have some maple sessions. 3 or 2:30? 2:30 is fine? 2:30. We can have maple session only. No lecture.
Okay.
Okay. I can show you some maple session, or he can show it.
Yeah.
So we need PDF file till now so that we can read.
No,
Sir, two black holes different from collision of two, per se, highly dense metal balls. But both of them produce, at the time of collision, a waveform that is equivalent to a Dirac delta function.
Well, first that you cannot have an astronomical object being a hard ball.
No, just a very crude approximation. Say. Because, for example, I was thinking.
No, I think that if you manage to construct an astronomical body, well, maybe a neutron star.
Yeah, maybe neutron star.
Say why black holes are different from neutron stars are not much, not very different.
No, from the point of observation of gravitational waves, sir. I mean to say, even when two normal metal bodies collide, they will also give a waveform that could be detected as an impulse.
Yeah, yes, if you manage, yes, but please bring me a hard ball of 13 solar masses. If you bring me something like that, then yeah, that would be the same.
Why not a general impulse be taken as a gravitational wave?
Sorry?
Why cannot an impulse be taken as a gravitational wave that is generated during collision?
Yeah, it can, but it depends on how big it is.
A small
Like
impulse?
I can have two billiard balls
Yeah.
somewhere in the intergalactic space and have them crash each other. That will produce a gravitational wave.
No, even
But
if the billiard,
extremely tenuous.
no sir, if a billiard ball, if they collide on this table
Sure.
itself,
If it collides with what?
if they collide on the table itself, it just
Yeah, you get gravitational waves, but
Yeah.
they're tiny. The intensity of this is tiny.
But they are very local, na? So they can't they be easily directed? I am having gravitational waves coming from so
Say,
far.
yeah, you have a
Yeah, I have a
gravitational wave,
Yeah.
but the signal is so weak that it's completely hidden in the noise, in our motion, in our breathing, in the motion of a mosquito here. It's completely hidden. But yeah, there is a gravitational wave there. Of course, gravitation, whenever there is interaction, there is a gravitational wave.
Seismic waves, aren't they gravitational?
Seismic waves will also produce gravitational waves, but they are so tiny, they are so small. Look, just think of it. It took people 40 years to detect a gravitational wave that was a fantastically catastrophic event at 1/2 of the age of the universe. Okay? But it was a very catastrophic effect. Now imagine that instead of that catastrophic effect, it would have been the collision of two billiard balls. We have never detected.
Maybe after lunch we can, because